The idea he proposed was as outlandish as it was revolutionary. The implications for the nature of matter were both perplexing and unsettling. That the electron could behave in ways that no one else could have imagined was troubling, not only due to the description's unfamiliarity, but also in that it implied the way physicists and chemists saw the world might be profoundly flawed. And yet, the explanation was successful at producing in mathematics what had been seen in the thin lines of the spectrograph. It solved a problem that had puzzled many, but in doing so, it raised many, many more. While Rutherford continued to probe the inner sanctum of the atom by shooting cannonballs at tissue paper, Niels Bohr tried to understand what was happening with the electrons, something he had been interested in throughout his dissertation work. What he came up with would finally move the scientific community to seriously consider the work of a pair of German physicists who had set out to understand how light and matter interacted and had introduced an idea that would end up changing the world. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series number 2, A History of the Atom. Episode 13, The Quantum Atom. To understand the work of Niels Bohr, the Danish physicist who would offer the first suggestions that the world really was queerer than we can imagine, we have to go back in time to pick up a thread we've so far neglected. While there is evidence that the prism had been used to study light as early as the Roman Empire, our story will pick up with Isaac Newton's work with light as published in his book Optics. Newton, as you may know, took sunlight and by shining a thin ray of it through a triangular piece of glass called a prism, found that it could be resolved into what is known as a spectrum, the rainbow of colors of light that runs from red on one end to blue on the other, as immortalized by the familiar mnemonic device learned by middle school students the world over, Roy G. Biv, or red, orange, yellow, green, blue, indigo, violet. Now, Newton had showed that these constituent colors could not be further resolved into parts, and thus established that white light was made of a combination of these colors. It was found that this continuous spectrum, as it was known, was emitted from all things that gave off white light, usually as they were heated to great temperatures. Now, in his description, Newton, who, as we've discussed, was a staunch atomist, argued that light was corpuscular in nature, made up of many small particles traveling in straight lines. Shortly after Newton's publication of this hypothesis, his contemporary, a man by the name of Christian Huygens, put forward a wave theory of light that supposed that light was some sort of a wave transmitting or traveling through space. Both men had evidence to support their ideas and could explain the observed phenomena in terms of their hypotheses. Unfortunately, in the mid-1600s, there wasn't a way to perform an experiment that would definitively distinguish between the two, and, as such, things would remain in a state of ambiguity until 1801. In that year, Thomas Young performed his famous double-slit experiment, demonstrating not only the wave nature of light, but that the color of the light was directly related to the wavelength, with red being longer wavelengths and lower frequencies, and blue being shorter wavelengths and higher frequencies. Now, as a quick side note here, in all waves, what we call wavelength and frequency are said to be inversely related. In other words, as the frequency of a wave gets bigger, the distance between the crests of the wave, what we call the wavelength, gets shorter. Now, the frequency can be thought of as being the number of times per second a wave goes up and down, or from maximum to minimum, and then back to maximum again. The faster this happens, which means you have a higher frequency, the more energy the wave is said to be transmitting through a medium. I'll post a diagram of this in the show notes. In the next year, 1802, physicist William Wollaston would observe that the sun's spectrum wasn't actually this continuous spectrum that Newton had observed. What he observed was Newton's continuous spectrum, but he also saw 6 or 7 dark lines interspersed within that spectrum. He was able to make this observation as the quality of glass being used to make prisms was improving, and thus allowing for clearer and more accurate observation. However, there were a number of issues that impeded further development of this observation. The first was that while improved, glass still contained way too many irregularities, especially if it was thick, to allow for very precise measurement. Second, since the spectrum was continuous, and thus the colors blended one into another, it was almost impossible to develop any sort of standard measurement system between one prism and another prism. However, within a decade or so, these issues were worked out by Joseph Fraunhofer. Now, Fraunhofer was a master craftsman when it came to glassmaking, and he's also trained as an industrial scientist. So Fraunhofer combined these talents to create prisms of unparalleled quality. In fact, he was so good at this, and he had his own recipes for making glass, that when he died, we actually lost the knowledge that he had, and glassmaking took a couple of steps back before sort of some of his techniques were rediscovered. Now, he used his prism to make a number of observations of different things, including, of course, the sun. To do this, he invented the first instrument specifically developed to observe and make measurements of spectra, something he called a spectrometer, and he did this in about 1814. Now, when he would use the spectrometer to observe the spectrum of a specific type of candle flame, he noticed that the flame produced a bright orange line in the spectrum and did so in the same place every single time. This allowed him to create an absolute anchor point from which he could make careful quantitative measurements. From this, he was able to make very precise observations of the sun's spectrum and was able to catalog over 500 dark lines in that broader rainbow of color. Over the next 15 years, Fraunhofer would continue to both make observations with and improvements to his spectrometer. In 1921, he would replace the prism in the instrument with something known as a diffraction grating, which didn't rely on passing the light through a piece of glass to produce the spectrum, and thus was free of the errors and uncertainties even the finest glass would introduce that way. Even with these improvements, the source of the dark lines in the solar spectrum remained a mystery. With Fraunhofer's invention of the spectrometer, a number of investigators began looking at light produced by a whole bunch of different processes, including the idea of dropping various salts into flames and light coming from sparks made from various types of metals. These results, collected over the next 3 decades, were sort of quantified and codified by 2 men. One was Gustav Kirchhoff, the other was Robert Bunsen in 1860. What these 2 found was that there were really 3 different types of spectra that could be observed depending on the type of light produced by the system being studied. The first type of spectrum was the continuous emission spectrum that we've already been talking about. It was produced by a hot solid or liquid, or in some cases if you had a gas under really high pressure. What they found is that the dominant color of this type of spectrum depended on the temperature of the substance, with cooler objects producing a spectrum that gave off light in the red wavelengths having lower frequencies. As an object got hotter, the peak wavelength would become shorter, moving towards the blue end of the spectrum. In all cases, of course, there's still a continuous spectrum of light being produced, but it was where the brightest part of that spectrum was that was changing as the temperature increased. The second type of spectrum was produced by a hot gas at low pressure. In this case, the gas emitted what was called a bright line or emission line spectrum. What this looks like is you have a black background with these very thin, bright lines at very specific places in the spectrum of different colors. The third type of spectrum they observed was produced when a continuous spectrum source was viewed after the light was passed through a cool, low-density gas. This produced what we called an absorption line spectrum, where there's thin, dark lines in that continuous spectrum, a lot like what Fraunhofer had seen with the solar spectrum. In determining these three types of spectra, Kirchhoff and Bunsen figured out two really important things. The first was that the bright line emission spectrum produced by each element or compound was always unique to that material, but was always the same for any sample of that kind of material. In other words, it was really a spectral fingerprint. For example, if you looked at the spectrum of a hot hydrogen gas through a spectrometer, you would always see the same thing: 4 thin, bright lines. 1 red, 1 blue-green, 1 blue, and 1 violet. If you then looked at the element helium, you would see a different set of lines that would always be the same for helium. The second thing they established was that the absorption lines for a given substance always matched the emission lines. From this, they were able to determine what was causing the dark absorption lines in the sun's spectrum. The surface of the sun was producing a continuous emission spectrum consisting with its temperature. The light of this spectrum was then passing through a cooler atmosphere that was absorbing specific wavelengths of light based on the elements that atmosphere was made of. What Kirchhoff and Bunsen didn't know, though, was how or why the line spectra were being produced. Known as Kirchhoff's laws of spectroscopy, these rules explained what was being seen, but they did not provide an explanation of how or why a specific element produced a certain set of spectral lines. They were a huge step forward in terms of classification, but they couldn't do very much beyond that. Still, they proved to be tremendously helpful for chemists when doing analyses of various compounds, as we've sort of already mentioned several times through the podcast. In 1885, the Swiss mathematician and physicist Johann Balmer realized there was a very specific mathematical relationship to be found in the wavelengths of the visible bright lines of the emission spectrum of hydrogen. What he found was that he could calculate the wavelengths of those lines using a fairly simple formula that depended on a single constant and integer numbers. A particular wavelength could be calculated by taking the constant, multiplying it by an integer, say 3, and then dividing the result by the difference of that integer squared, 9 in this case, and the number 2 squared, or 4. Doing the calculation I just described would result in a wavelength of 656 nanometers, which matched the red line of the visible part of the hydrogen spectrum. Using 4 as the integer gave the blue-green line's wavelength, and so on. This expression, rather Pythagorean in its form, was generalized by the Swedish physicist Johann Rydberg 3 years later in such a way that it could be applied to predict where all the spectral lines produced by a hot hydrogen gas would be, including those in both the infrared and ultraviolet parts of the spectrum. Again, while the reason for this irregularity was unknown, the fact that the wavelengths could be represented with a simple mathematical relationship strongly suggested a deeper underlying cause, something physical, for the structure of the spectral lines given off by the elements. Of course, there were those who had already glimpsed this possibility. As we discussed in the episode on the periodic table, Gustav Heinrichs at Iowa State used the regularities in the spectra of various elements to help guide his construction of one of the earlier periodic systems. And while Mendeleev himself was sort of opposed to trying to find a more fundamental cause for the structure of his table, Lothar Meyer was much more amenable to that kind of idea. By the mid-1890s, just prior to Thomson's discovery of the electron, there were those in both the physics and chemistry community who felt that the spectral lines were associated with the electrical properties of the atom. Heinrich Lorentz already well known for his mathematical work on the wave nature of light and attempts to rectify the seeming inconsistencies of Maxwell's electromagnetic equations with Newtonian classical dynamics, suggested that the spectral lines might be caused by the motion of electrified particles in conjunction with the atom. This view was bolstered by the observations of Peter Zeeman, who showed that single spectral lines could be split into multiple closely spaced lines when a gas was heated in the presence of a strong magnetic field. When Thomson discovered the electron, it lent strong credence to these ideas and resulted in the dynamical structure of both Nagaoka's model and his own in terms of their electron placement. As noted in the New Models episode, when it was shown that the Saturnian model was unstable, Thomson's model was left as the best explanation of the structure of the atom, not just because it was more stable, but because it also offered the best promise of being able to explain the production of spectral lines. Of course, the scattering experiments done by Rutherford's team in Manchester definitively showed that the plum pudding model was inaccurate, but it also reopened the question of what was going on with the atom's electrons. The nuclear model was put forward to explain the scattering results, and thus more or less ignored what was happening with the electrons, a weakness Rutherford fully acknowledged in his papers announcing the new model. The gateway to the solution for this problem was to come from the mind of a supremely talented young physicist named Niels Bohr. As I plan to do a supplemental episode on Bohr, I'll leave the biographical details of his life to that and focus here on his specific contributions to the matter at hand. Bohr had done his PhD research on electron theory as it related to metals in 1910, and so it made sense that his postdoctoral fellowship work would be with Thomson's group at the Cavendish. However, it turned out that he didn't really click with the research program there. And so when he heard Rutherford's speech at the lab's Christmas celebration in 1911, he was taken by the great man's passion and vision. A few weeks later, he traveled to Manchester for personal reasons and dropped by to meet Rutherford personally. The two men talked about the work of Max Planck and Albert Einstein, and through the conversation, they got to know each other and decided it would be better for Bohr to finish his fellowship at Manchester. So, in the spring of 1912, Bohr joined Geiger's group and got a quick crash course in radioactivity and the new model of the atom that was being used at the lab. So, what did the two physicists talk about in that first conversation? Why was the work of Planck and Einstein so important that it formed the basis of one of the most consequential chats in the history of physics? Well, it had to do with light. Back in the 1890s, one of the outstanding problems in classical physics was that the present theory that was being used couldn't explain how a heated solid object produced that continuous emission spectrum we've been discussing. Whenever somebody tried to derive an expression that modeled the spectrum well using the accepted wave theory of light, the model worked great for long wavelengths, but it sort of blew up at short wavelengths. The problem, known as the ultraviolet catastrophe, was that the mathematical model predicted that the object would give off increasingly larger amounts of energy at shorter and shorter wavelengths instead of tapering off as was observed in spectra for real physical systems. In fact, as the wavelength was shortened into the ultraviolet part of the spectrum, now remember, as you move towards the bluer end of the visible spectrum, the shorter the wavelengths get. So, ultraviolet light is made up of very short waves with high frequency. So as you move to that part of the spectrum, the amount of energy the model said an object would give off ended up approaching infinity. That's a real problem. No matter how the physicists tried to fix the model, they couldn't get rid of this problem. At least not until the German physicist Max Planck tried something really radical in 1899. He seems to have gotten the idea from the work of Ludwig Boltzmann, though there's some debate about that among historians of science. Boltzmann, if you recall, was one of the physicists, along with Maxwell, that developed a fully mature kinetic theory of gases based on not only an atomic model of matter, but on a model where the properties of those atoms could be represented statistically and where energy was said to come in discrete specific bundles. Now, this approach had bothered Planck quite a bit, and when at a conference he expressed his disagreement to Boltzmann, the younger physicist responded that not only did he see the approach working with matter, but that it also might be possible to discretely bundle energy in other situations as well, and that similar techniques could be useful to solve all their problems. Not long after the conversation, Planck decided to develop Boltzmann's offhanded idea to treat the continuous emission spectrum problem. To his surprise and a bit of chagrin, the method worked tremendously well. This bothered Planck a lot because he thought that energy was continuous, but to solve the problem, he had to make this assumption that energy came in discrete little bundles, things that he called a quantum of action. While pleased with the solution to a problem that had stubbornly resisted their efforts, the physics community seems to have overlooked at the time the physical meaning of the way in which Planck got around the difficulties the solutions that assumed light was a wave had run into. Planck himself saw his solution as little more than a mathematical trick, or mathematical fiction as he sometimes called it, that was needed to solve the problem, and the broader physics community was happy to go along with that explanation, at least until Einstein came along. Einstein, as many of you probably are aware, was working as a clerk in the Swiss Patent Office when he became intrigued by a problem that had been around since about 1839, though Heinrich Hertz had most fully described it in 1887. It was known that if one were to shine a light on a piece of metal, the metal would produce an electrical current. What had been observed was that if the wavelength of the light was short enough, or, to put it another way, if the frequency of the light was high enough, above a certain threshold frequency, the electrical current was produced in the metal. If the frequency was below the threshold value, no current was produced. Additionally, whether there was a current or not didn't depend on how intense the light was. That only affected how much current was produced, if any current was produced at all. There was no way to explain this phenomenon, known as the photoelectric effect, using the wave description of light. What Einstein did was take Planck's idea of quanta and apply them to this problem. He said that light had to come in bundles of energy he called photons that acted as particles just as they also acted like waves, in saying that the energy of the particle could be calculated from its frequency, something light had to be a wave to have. Einstein said that if the particles of light, the photons, had enough energy, they could knock electrons loose from the metal, which would then form the observed current. Since frequency and energy were directly related, that meant if the frequency of light was high enough, then it had enough energy to knock the electrons loose. Einstein's mathematical treatment of the system worked perfectly, but in explaining the system, it created a whole new issue. In the Young double-slit experiment, light had been conclusively shown to be a wave. Einstein's explanation of the photoelectric effect required light had to be a particle. Waves are things that are spread out in space. Particles are things that are found in one place in space. Therefore, light seemed to be showing that it had both qualities. It was a photon with a wavelength. Einstein called this behavior wave-particle duality, and it threw the physics community for a huge loop. This was something that classical physics did not allow for, and yet, there it was. This also made it clear that energy, at least in the form of light, came in quanta or discrete bundles. In 1905, no one knew what to make of all of this. In 1912, Bohr was working with the group in Manchester, trying to help them make sense not of the nucleus, but of the electrons that seemed to be orbiting in it. Classic electrodynamic theory required that the electrons, if they were traveling in circular orbits, give off electromagnetic energy and spiral into the nucleus. Now, obviously, that wasn't happening, so why not? This was the first question Bohr was trying to answer. A second question was that he wanted to see if he could get Rutherford's model at least on par with those of Nagaoka and Thomson in trying to explain how the bright line emission and dark line absorption spectra were being produced. After about a year of work, he had his answer, and it was groundbreaking in its brilliance, but also troubling in its implications. What Bohr did was start out with the simplest type of atom he could, the hydrogen atom. This was a good place to start because since it only had one electron, he didn't have to worry about multiple electrons interacting with each other. Bohr said that the electron couldn't just orbit the nucleus at any old place or in any old way. He said that there were specific distances from the nucleus that he called energy levels where the electron would orbit and would do so without being unstable or losing energy. Now, when I say, quote, he said, unquote, what I really mean is that he put forth the idea and then supported it mathematically by using the deductive reasoning inherent in working out the math to demonstrate the consequences of his ideas. The most profound consequence was that he was able to mathematically derive what the emission spectrum of the hydrogen atom would look like, and he got exactly the Balmer-Rydberg equation and that constant from his work. So how did it work? Well, this is where things get really bizarre. The electron is only allowed to orbit the nucleus at a given energy level. It can, however, change energy levels. To do so, it has to gain or lose exactly the difference in energy between the two levels. A great way to think about this is if you were on a step stool with 3 or 4 steps. Now, the higher you are on the step stool, the more stored, or what we call in physics, potential energy you have. This is how the energy levels worked in the atom. The further away the electron was from the nucleus, the more potential energy it had. In physics, there's this thing known as the law of conservation of energy. It says that you can't just create or destroy energy. You can only get it to change form. So going back to our analogy, for you to move up a step on the stool, you need to get some energy. If you want to move down, you would have to give off some energy. The same thing would be true for the electron orbiting a hydrogen nucleus. If the electron was in the lowest energy state, usually what we call the ground state, and it absorbed some energy, it would jump into a higher energy level. If it were in a higher energy level, it would give off energy and drop into a lower energy state. The thing was, however, that the electron couldn't just absorb any amount of energy and move to being further away from the nucleus. What it had to do was gain the exact amount of energy that separated the two energy levels. Remember, Bohr said the electron was only stable in those specific energy levels, and thus would only be found in them. Thus, the electron had to jump the exact energy difference, not any more or any less. If the electron dropped to a lower energy level, it had to give off the exact amount of energy that was the difference. Again, from our step stool example, you can't just move up or down half a step. It's all or nothing. So where did the energy come from or go to? This is where the dark line absorption and bright line emission spectra come into play. Shining a continuous spectrum through a cool gas produces the first of these. Using Planck's idea of light coming in quanta or discrete packets of energy, Bohr was able to say that since this was a continuous spectrum, there were going to be some packets that had just the right amount of energy for the electron to absorb and then jump up a level. When the electron did that, the photons at that energy would now be missing, and that would leave a dark line in an otherwise continuous spectrum. Electrons transitioning down from higher energy levels to lower energy levels form the bright line spectrum. That transition would give off a photon of the exact energy difference, which would produce a very specific bright line at the wavelength that corresponded to the energy. Now, what was even more bizarre, though, was that Bohr said that when the electron transitioned from one energy level to the other, it couldn't actually travel through the space between the energy levels. It would have to disappear from one level and appear at the other, because if it traveled through the space, it would have to either spiral in towards the nucleus or out away from the nucleus, and thus give off a continuous spectrum that didn't match what was being observed. One way to think of this, and it's a really crude analogy at best, I think, is to think of getting in your car to travel somewhere. Here where I live, there's a bigger town about 20 miles north of me with two small towns in between. Now let's say I wanted to travel to the big town, but I have to behave in this quote-unquote quantum fashion. In order to get there, I would get in my car and rev the engine just the right amount, and I would instantly be in the next little town to the north. If I rev too much or not enough, I don't go anywhere. If I then rev a somewhat different, but again, right amount, I jump to the next little town north of the first one. If I was clever, when I was in my driveway, I revved the engine just the right amount that was the sum of the two energies, I would jump straight to that second small town. The important thing is that I wouldn't have traveled on the roads in between the towns. That's pretty weird, right? Now, as this is a pretty complicated description, I'll be sure to post some links out to a few simulations that illustrate how all this works in the show notes at thescientificodyssey.typepad.com. There really are a number of good sites that will show you not only how these electron transitions happen, but that will actually allow you to sort of build your own energy levels for the atoms so that you can get a sense of how all of this takes place. For the real nerds or geeks out there, you can even play around with the simulations while watching an episode of your favorite group of physicists at Caltech and their hijinks and escapades. Back to our story. When Bohr published his ideas in 1913 in a trilogy of papers, he was understandably met with some real skepticism, which is a good thing. His model of the atom had some pieces that were based in the realm of classical physics and other pieces that were taken from the quantum ideas of Planck and Einstein. What made things worse is that Bohr had this sort of maddening habit of not always working things out from first principles mathematically. His paper was a mathematical tour de force in deriving the spectrum of first the hydrogen atom and then what we call the singly ionized helium atom. But to justify his leaps of reasons, he sometimes appealed to the very spectra he was trying to explain. So, not only was his explanation deeply non-intuitive, as a physicist might say, but it was a little bit circular in its reasoning at times. So, why was it accepted, especially among the younger physicists? Well, as this thing that we always talk about when it comes to quantum mechanics, why do we think quantum mechanics is true? The answer is because it works. It may not make sense, and in this case it may not have made sense in some regards, but there was no denying that it offered the first really good way forward in understanding the behavior of the electrons around Rutherford's nucleus, as well as explaining where the two types of line spectra came from. This planetary model, as it's been called, did have a number of problems, however. The biggest issue is that it didn't explain spectra for multi-electron atoms very well. It also didn't explain the splitting of spectra lines in magnetic field, that thing that we were talking about earlier called the Zeeman effect. But what the model did do was give many in the physics community, especially the new breed of theoretical physicists, a really good jumping off point in their investigations. One additional point should be made here as well. In our discussion of the atom, this is the first time where an almost purely mathematical approach had been taken in order to understand the atom and its structure. This was part of a huge shift in the way physics was done at this time. The shift had sort of begun with Maxwell and his equations of electromagnetism. They had continued through Boltzmann in kinetic theory of gases, and then through Planck, and was embraced by Einstein in his 4 famous papers in 1905. This movement towards an equivalent role in science to a theoretical development of ideas has its roots in the work of Hans Ørsted in developing a description of scientific inquiry in the 1920s. and it marked the transition from classical physics to modern physics as much as Einstein's theory of relativity and this development of what we call quantum physics did. Now, at this point, we need to bring the episode to a close. While Bohr's model is a big step forward, there are a number of other developments taking place either just before or right at the same time that will give insight into what is going on with the electrons in the atom. Furthermore, there'll be a number of early modifications to the Bohr atom over the war years and just after that will raise a number of deeper questions about just what the implications of a quantum approach to matter really were. Now, before I do that, I'd like to do another supplemental episode, this time on the life of Niels Bohr. At least, hopefully I'll be able to keep it down to one episode this time, before we move forward in the narrative. So, after this podcast, next week, I'll try to have an episode on Bohr out. Also, we're starting to get close to the end of the series of the podcast, and that means we're getting close to what I hope will be our first question and answer episode. I've had a couple of questions sent to me already, but I'd sure like to get several more. The material we're getting into now often generates all sorts of how and why inquiries, and I hope you'll send me yours if you have them. While I'd like to focus the questions episode on the history of the atom, anything you want to ask is fair game. So ask away in the comments section for this episode, either at the website or at the podcast Facebook page. And as always, thanks for listening. And until next time, full sails on your journey.